Hello everybody, Whiteboard Economist here, and welcome back to my channel. This is my next video on my series for Calculus 1. And you can see on the board here that the topic for this video is derivatives as a function. What I mean here is we're going to take the derivative of a function and then take a function from that derivative. So if you recall from the last video, we went over the definition of a derivative. And so this equation should seem familiar to you. F prime of a is equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. Now what this equation does is it will tell you the rate of change of a function at certain points. For example, if I had a function f of x, something of whatever right here, then I wanted to find the rate of change at say point 2 or f of 2. All you have to do is simply sub in a 2 for the a here, and then sub in a 2 every time you see an a on this side. And then that will spit out a number, and that will be the rate of change of this function at point 2. Now, if I wanted to find the rate of change at point 3, then you're going to have to erase this 2, put a 3 here, and then sub in a 3 here, and go through the entire process again to get the rate of change at point 3. Now, let's say if I wanted to take the rate of change at point, I don't know, something like 9 to the 52nd power. Now that is a big number, and if you sub it in for here, that's going to be an unpleasant equation to solve for. And not to mention, it'll get kind of annoying to solve for the rate of change at 500 points on the line. And so this equation here can become a bit cumbersome. So what do you do to solve this problem? Well, instead of taking derivatives at certain points, why not just write a function for the derivative and then just simply plug in points for x and make this a one-step process? And that's exactly what we're going to do today. So the first step, of course, is to realize that f prime of a, the a here denotes a constant. And since we're trying to find a function, we need a variable instead of a constant. Now, how am I going to show this is I'm going to replace the a with the letter x. And of course, over here, replace the same thing. Now, you're probably asking, well, what was the point of that? Because all I did was replace one letter with another letter. Now, the important thing is not so much, that I replace the letter a with the letter x. The take-home concept is this used to be a constant. Now it's a variable. And since by mathematical convention we denote variables by the letter x, that's why I wrote an x here. So it's not so much the letter change, it's the fact that this is now a variable instead of a constant. So now let's see this in action here, shall we? So let's say we wanted to find the derivative of a function f of x equals x cubed plus x. So going by the definition, you have f prime of x is equal to the limit as h approaches 0 of something over h. And this something right here is simply f of x plus h minus f of x. But how do you find these values? Well, f of x is already given to us. F of x is equal to x cubed plus x, so obviously it's going to be minus x cubed plus x. So how do you find f of x plus h? Now recall from my earlier videos that I made it very clear that whatever goes inside these parentheses doesn't really matter as long as it stays consistent on the other side. So to convert these two, all you have to do is simply plug in an x plus h for every time you see an x here. So f of x plus h simply becomes x plus h cubed plus x plus h. Now, it seems that all I did was make this function a bit more complicated. So how is this going to help me find the derivative of x cubed plus x? Well, notice here that x plus h cubed is simply a shorthand way of writing x plus h times x plus h times x plus h. So if you multiply all of this out, you should get a new function f prime of x is equal to the limit as h approaches 0. If you multiply this entire thing out, you should have gotten x cubed plus 3x squared h plus 3xh squared plus h cubed. Now plus x plus h, and minus x cubed plus x. Now of course the negative distributes out, so that becomes negative x cubed minus x, all over h. And again, it just seems I made this equation more complicated. But notice that some of the terms cancel out. For example, x cubed minus x cubed, that cancels out, so you can just erase this from the equation. And now you have plus x minus x, so these two cancel out, and now you're left with the terms 3xh plus 3xh squared plus h cubed plus h. Now the next thing you'll notice that each term on the numerator has an h value in it. So you can simply pull out an h, and h now becomes 1, so plus 1. H squared becomes h, h cubed becomes h squared, h squared becomes h, and then h becomes 1. And now you'll notice that there's an h on the numerator and an h on the denominator, so the h's here cancel out, and now you're left with this equation right here. It doesn't seem so bad now. But we were going to make it even simpler because we have limit of h approaches 0. And so what this means is h is eventually going to become 0. So you can simply replace 0 for h on this equation. So it becomes 3x times 0. That cancels out because anything times 0 is 0. Plus 0 squared, which is also 0. So you're left with the conclusion that the f prime of x is equal to 3x squared plus 1. So if you wanted to find the rate of change of this function at point 2, you simply put a 2 in here and then plug in 2. So 2 squared is 4, 3 times 4 is 12, so the rate of change at point 2 is 13. If you wanted to find the rate of change at point 3, then you simply put in point 3, and that becomes 3. So it's a much quicker process than going through this entire thing. Alright, so this is how you would find the function of a derivative. This was a relatively simple example here. In a future video, we're going to go through some more examples. We're going to do some practice problems, but today I just wanted to give you an introduction on how to find the derivative of a function and then express that derivative as a function itself. Alright, anyway, so that's all I have for this video, but I hope you enjoyed watching it and found it informative and learned something from it. But anyway, that's all I have for today, so as usual, have a nice day.